So what we have discussed so far are about the Boolean algebra. So there we were discussing the mathematics of logical variables, which can be either true or false or high and low, and we have set up some operations, logical operations like and or, which are the basic operations, and we saw that there are some theorems which are true. So those theorems are always valid for logical variables which are being operated with logical operators. Then we from that understanding, we also developed a further understanding of logic gates, where given two logical variables, we saw that the combinations of them could lead to some type of outputs, and obviously the AND operation between these variables and the OR operation between these variables are well known to us. But we also discovered that there are few more operations which can be possible, which we where the well, also the complement operation or the NOT operation was also there, and these few more other operations which we discovered were the NAND, NOR, XOR and XNOR operations, and those operations are called gates. And we had a symbol also, we came to know the symbols to represent these gate logics. So those understanding were in the abstract level, and in this lecture we would try to see how that abstraction can be physically realized. So there are several ways of realization of that abstract concept of gates. As in that video I had shared, you had noticed that it all started with mechanical switches, then vacuum tubes. So those sort of switches were used to implement the logic circuitry, and that to implement the gates, the logic gates. However, as time progressed, the discovery of transistors led to an immense possibility of reducing the size of these switches, and there we can actually incorporate a lot of gates in a very tiny amount of space. So that actually was another breakthrough that uh, carried forward the invention of computers, and those are the electronic logic gates. It is called electronic logic gates? Because they are these logic gates are implemented using electronic circuitry, the electronic circuitry of the transistors. So we are utilizing the characteristics of transistors, the inherent behavior of these devices, the transistors, in order to uh, 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 in order to implement, or in order to build the switches required to generate the operation of the logic gates that we have studied. So the basic action of the transistor that we would be utilizing is the switching action, so that the transistor either passes as a current through it, or it blocks the current, depending on what it is seeing at the gate. So that idea, that switching and its operation as a switch, that idea would be utilized in order to construct the logic gates. Let us go into this lecture and see what we have to discover. The first thing that we would study are the logic levels. Now you see what actually happened, what actually happens in a computer. So if we have a so if we say that the computer is basically a arrangement of transistors, because the transistors are the switch elements which we are using, they are the basic elements we have to use. Now these transistors or whatever we have, we know that everything is actually, these things are actually working in some analog voltage and current. So the values of voltage and current can ideally vary from minus infinity to plus infinity, though we know that there is a range of operation, but the idea here is that this is a continuous range. So there is no 0 voltage or 1 voltage. So we don't have 0 volt exactly, or we don't have 1 volt exactly, right? So what do we actually do? So we actually have a range of voltages uh, varying maybe from like -5 and to +5, and this also, you know, if you have done experiments, that it may be -5.23 or something like that, and there can be many other places of decimal which we can actually get here, and it says same thing happens for +5 also, +5.51 something can be there. So this range is very dicey in nature, because we don't get an exact value of voltage at any time. So at any time you measure, you are getting a voltage, but at the next instant that voltage is changing. So this sort of small changes keeps on happening in the within the transistor, when we are actually trying to measure the voltage, we are noticing these sort of changes. So this makes any sort of computation using these numbers, so using these voltage values, if we want to make any computation using the voltage values, then that computation will be inaccurate. Because suppose I say that I want to do 5 plus 3, then you say, okay, I am giving you a 5 volt and I am giving you a 3 volt, then in the circuitry you add them up and you will get the result. So that can be an addition circuit. So you have a voltage, so how you add up voltage? So you have a voltage here between these 2 points, and then another voltage you have between these 2 points. So if you have to add up these voltages, then you would connect these two and then measure the voltage between these 2 points, right? This would give you this V. If this is V1, this is V2, this will give you V1 plus V2. Of course it will give you V1 plus V2, but if you are trying to do a computation with exact values, the computation must happen with exact values, right? But what is coming here as V1 and as V2, you are saying that okay, I have supplied 5 and I have supplied 3 here, so I will get 8 here. But when you measure this V1, you will not get a 5, you will get something which is rapidly changing within some range. Here also you will not get a 3, it will get something which is rapidly changing, and here also you will not get a 8. So this sort of addition circuitry will not work. So the analog arithmetic operations, which you may be studying in another course in this particular semester only using op-amp circuits, they of course they are adding voltages, they are subtracting voltages, those operations are happening, but since they are analog in nature, we cannot rely on the accuracy of the result. They are adding voltages, so if you need to add voltages, you can use that adder. But if you need to add numbers, if you need to add accurate measurements, then you will be not able to use that particular circuit. So this sort of accurate computations is what we are interested in when we are trying to use a computer. This accuracy is not present in the analog paradigm. This accuracy is absent in the analog paradigm. But if we are able to map this analog range of voltages etc. to only two single digits, which are 0 and 1, only two bits 0 and 1, then we can form a string of binary words with these bits, which will be either 0 and 1, and we will get an exact and accurate computation we will be able to perform. So if you are able to have 5 places, so several places with you, and each of these were having some analog voltage here, but by doing some trick you can either have 0 or 1 in these places. So instead of the analog value of the voltage, you are seeing 0 or you are seeing 1. Then what you can do, you can actually, any number or any value that you are given with, you can encode that value in terms of zeros and ones and obtain a binary word. Like 5, 5 will be 10101. So suppose these two are not here, or we don't need this here. And for 3 we use this set of 4 places here, which are called bits, and we set up the voltages here in such a way that we get a 0011. So we have to do this setting up of the voltages in some way, so that whatever be the voltage here, the inaccurate voltage now is read as 0. The inaccurate voltage here, the inaccurate analog value of the voltage here, is now read as 1. So now we get these binary words, and then what you will do, then you can add them up. By passing them through some circuitry which is able to perform addition operation. However, we let's not bother about that addition circuitry right away. Let's just bother about obtaining the values, obtaining these quantities which we want to compute with each other. So that obtaining of these quantities is the first step that we should be bothered about. So that happens only when we are able to do an operation like this, which transfers the entire analog range to only 0 and 1. Okay, and this is basically simply an assignment. So here we are only concerned about labeling a particular range of voltage as low and a particular range of voltage as high. So we don't need to have an exact value of the voltage, but a voltage within a particular range can be classified as high voltage, and a voltage at a particular range of in a particular range can be classified as low voltage. And whenever we are seeing a low voltage, we interpret that low value as 0, and whenever we are seeing a high voltage, we interpret that high value as 1. So this interpretation has to be done. Then what happens? The entire analog range of values which are inaccurate in nature becomes something accurate with which we can do computations. So we need to know what are these range of voltage values which we label as low and high in a transistor. Of course, this is what is a we are talking about transistors. Okay, so we would look into the transistor. So the transistors, you know that so this is a logic device, that is a logic gate, and the logic gate can be built using CMOS transistors and the TTL logic. So this is a transistor logic. There is also a DTL logic, which is the diode transistor logic. So with all these systems or all these types of transistors, you would be able to build logic gates. For logic gates made with CMOS transistors, CMOS devices, so I guess in your analog electronics class you have studied the BJT, you have studied the FET, maybe you have also studied the MOSFET also. CMOS is also a certain type of transistor, and these are the latest one or the most modern one which are in use, and we will actually study the CMOS logic gates. So if you don't know the exact detail of CMOS, you don't need to worry. You just need to understand how a transistor works. All these CMOS, whatever, be it CMOS, be it simply MOS, be it simply FET or BJT, they all have the same principle of working. Just their internal structure, the material is used to manufacture them becomes different, which leads to some improvement, etc., in the operation. That's all. So the CMOS is what we will be actually concerned with. And in this CMOS, as you see in the table, the range of voltages from 0 to 1.5 is considered as low, and the range from 3.5 to 5 is considered as high. So why this range has been chosen? Because it is in the experience that when the CMOS transistor is off, then the output varies from in this range perhaps. So, and when it is high, the output is varying within this range. And in BJT, the output is varying within this range when it is off, and within this range when it is on. So that's why these particular ranges are chosen for the assignment of low and high. Now if we are assigning low as 0 and high as 1, then we are working in the positive logic system. When we are assigning low as 1 and high as 0, then we are working in the negative logic system. This we already had discussed before also. Now you note that between this highest value of the low level and the lowest value of the high level, there is a gap. So this gap is an undefined logic level, and if the voltage value is somewhere there, then what you can interpret can be either 0 or 1. Both things you can interpret. However, in the normal operation of the transistors, when we are operating them operating them as switches, so either they are in the low range or in the high range at the steady state. So when they are between 1.5 to 3.5 is the transition state. Suppose it is being made on from an off state, obviously it will go through all these voltages. However, the transition is very negligible. The time of transition time is very negligible. It is in the order of 10 to the power of -9 seconds. So we can ignore that. So this confusion whether it is 0 or 1 can be ignored for most of the practical purposes. What are buffer circuits? Suppose in an operation you are seeing that I am nearby 3.5. Suppose I am at 3.6 or 3.7. Now you know that since the analog voltage can keep on varying, so it can so happen that that 3.6 suddenly becomes 3.4, and then you are confused whether it is 0 or 1, whether it is high or low, because when it is between 1.5 and 3.5, then it can be 0, it can be 1, both can be happening, and you don't know what to actually take. So for those reasons, what happens, we actually build buffer circuits. The aim of the buffer circuit is to push the voltage levels towards the extremum values. That means if you are in the lower range of the high voltage, then the buffer will push it towards the higher range of the high voltage, and if you are in the higher range of the low voltage, then the buffer will push you to the lower range of the low voltage. So they will push you towards the extremum values. So these are the buffer circuits. There are some circuits called buffer circuits, which basically does not change the output logic level. It does not change the output logic level, but it changes the output analog voltage, so that the voltage goes towards the extremum values, so that the logic is steady, so the logic remains safe, so it does not fluctuate. The logic level does not fluctuate because of the fluctuation in the analog value. So that is the work of the buffer circuits. And I hope you remember that I had shown you a symbol like this when we are studying NOT gate, and I told you that the signal here remains same, and this is a logical variable. So if it is high or low, this is also high or low. This thing is called a buffer gate, or simply a buffer. The work of this is not to change the logic level, but to push the logic level towards the extremum values. Extremum, I can write here analog, extremum analog values. This is the work of the buffer circuits. Now there are some other problems associated with transistors. We know that if you keep a transistor without anything connected at its gate, without any specific voltage connected at its gate, then it is called the floating input problem. So the input is floating, we don't know what exact voltage is there, and since these are very sensitive devices, due to any electrical disturbance or any electrostatic disturbance, there may accumulate some charge at the gate, and it can recognize it as some voltage, and which is high. It can recognize it as some high voltage, or it can recognize it at some low voltage, and this recognition can also keep on changing. So what will happen, depending on that floating value, the output will always be, we will always generate some output if the transistor has some power. So the output will keep on changing also. We don't want this sort of a situation to happen, so we need to avoid this situation. To do that, what do? We always keep the input connected to some logic level, either high or low. We always keep the input connected to some logic level, either high or low, till the time a logical variable or a signal which is 0 or 1 is appearing at the input. So when this signal appears, then this signal is treated as the input to the transistor. However, when the signal is not connected, then by default it is connected to either high or low. So if it is connected by default to a high voltage, that means the VDD source voltage, if we are connecting it by default to the source voltage, then we use a resistor to connect it to the source voltage, and this resistor is called a pull-up resistor. This resistor is called a pull-up resistor. So suppose it is like this, you have your transistor, something like this, and I guess I don't remember so much how to draw the transistors. So this is the gate side, and I guess this is one VDD is connected and another can be connected to the ground, and this is the output that you are getting. And this gate is connected through a switch. So this is a switch, and here you are supplying your signal. Now if this switch is connected, of course this is the signal it recognizes at the gate, but when it is not connected, the gate is floating. So that situation we want to avoid, and if you are using a pull up resistor, then the pull up resistor appears between the VDD and the gate and the gate input. So what happens, it always when nothing is connected, it recognizes a high voltage at the gate, and accordingly it is switched on or off depending on the nature of the transistor. So whether it is on if the gate is high, or whether it is off if the gate is high, depending on that particular nature, this transistor's behavior is obtained, the output is obtained depending on that. Sometimes what we do, we use a pull down resistor. So when we use a pull down resistor, then we have to connect the resistor to the ground from the gate. So when nothing is connected, when no signal is coming here, then the ground voltage is appearing at the gate. Okay, once the signal is connected, then this gate voltage becomes the voltage of the signal. It does not remain ground because it is not shorted, right? It is connected through a resistor. So the signal of A is actually shorted. So the signal A will come at the gate. So I hope this pull up resistor and pull down resistor idea is clear to you. So we always use a pull up or pull down resistor in transistors to connect the gates, so that there is no problem of floating input appearing. And this is very important when we are using the transistors to construct gates, because we have to be very certain that the output is either 0 or 1 and it does not keep on floating. It does not keep on changing between 0 and 1. We have to be very certain about the output. Now the next thing that we want to understand about the logic levels is this simple fact: the correspondence between positive logic and negative logic systems. So we are working with the gates which are AND, OR, NAND, NOR, XOR, XNOR and NOT. So these are the logic gates that we are using. So now there is a correspondence between the positive logic gates and the negative logic gates, and the correspondence is written as you can see. The positive logic AND gate is the negative logic OR gate, and vice versa. Similarly for NAND gate and NOR gate, XOR gate and XNOR gate. So the positive logic AND gate, so let us just see why this is true. So that if we have to construct the AND gate, this is the truth table of the AND gate. This is the truth table of the AND gate. Now suppose this is positive logic. Obviously this is positive logic. If you are changing the logic suddenly, if you are, suppose you are changing the logic to negative, then what happens? You remember that this 0 has appeared because there is a low voltage, or there is a low logic. That's why you are writing 0 here. The low logic is a low voltage actually in the hardware. In the hardware, in the physical thing is the voltage. The physical measurement is the measurement of the voltage. So so there is a low voltage, that's why you have written a 0 here. Now if you want to transfer this same truth table to a negative logic system, then the low voltage is encoded as 1 and the high voltage is encoded as 0. So the low voltage which was appearing here, so in place, basically in place of 0 you will write 1, and in place of 1 you will write 0. So you write 1 in place of this 0 in positive logic, because now the low voltage is encoded as 1, encoded as high, the low voltage is encoded as 1 and the high voltage, here was the high voltage is now encoded as 0. So now you look at this truth table, and this truth table is nothing but this was the AND. This was the AND. This truth table is nothing but the OR. The truth table for OR. Remember, AND and OR logic operation remains the same. The idea remains the same. If you have true and false, then here only if any one of this is true, then the output is true. This remains same no matter what logic system you are using. Here if both has to be true, so that the output is also true. This is the AND logic. The OR logic is any one of the input can be true, then the output is true. That is the OR logic. So the OR logic is appearing here. That means what is AND gate in the positive logic system is behaving as an OR gate in the negative logic system. It is the same gate. It is the same gate, because this operation, whatever gate, whatever arrangement of circuit, whatever arrangement of electronic circuit is giving you this truth table, if you change the logic system suddenly, the same arrangement of physical hardware, the same arrangement of electronic elements will give you this truth table. The actual operation of the analog devices, the electronic components, the actual levels of the voltages will all remain the same. But since your logic system has changed from positive to negative, you will interpret it differently. So the change happens in your interpretation, and the change happens in this way, that what was the AND logic gate in the positive logic system becomes the OR logic gate in the negative logic system. Similarly, if you draw truth tables for OR in the positive logic and change the logic system to negative logic, you will see a AND gate truth table coming up. Same for NAND and NOR you can observe, and for XOR and XNOR also you will be able to observe that. This has huge implication. What is the implication? The implication is this, that if you want to use negative logic system, you don't have to build a different circuit for implementing its gates. The circuits are already built for the positive logic system. You only have to use the AND gate circuit when you are trying to implement a OR logic in negative. So whatever has been built for the positive logic system, the AND, OR, NOT, NAND, NOR, all these gates, you simply have to use the alternate gate. So if you are trying to implement the OR logic gate in negative logic system, you have to use the AND gate of the positive logic system and pass your signals through it. You will get your OR operation. If you needed to implement the XNOR gate in negative logic system, you take the XOR gate of the positive logic system, the same hardware you take, the same connection of transistors you take, and you pass your signals through that, you will get the XNOR operation in the negative logic system. So this means you don't need to construct new set of circuits for the negative logic system. So that is the implication. So only a particular set of circuits that you have already made for the positive logic system will also be able to, you will be able to utilize them to operate in the negative logic system as well. So now we will look into the actual connection of the transistors in order to form the gate circuits. So these gate circuits we will look into, and we will look as a connection of transistors which are giving the, which is bringing out the gate operations. So remember that the gate operations are fundamental in digital logic circuit design. The gate operations are fundamental. The truth tables of the gates are fundamental. However, these fundamental devices which are the gates can be constructed in so many different ways by utilizing switches. The switches that we utilize in our modern computers are the transistors. In earlier days, mechanical switches were also used, vacuum tubes had been used. So any sort of switch can be used and made a gate. But now we are only studying the gates made by Cmos transistors. Only that we will study, because these are the ones which we utilize nowadays to construct our logic circuits. So these are the type of gates which we utilize. So that's why we will study these only. So the first gate we study is the NOT gate, and here you understand this symbology of the CMOS logic gates. So here this side you can understand this is the gate, and this is your connected to the source, and this is the collector. And so if you see a bubble at the gate, if you see a bubble at the gate, this means this transistor is switched on, or this becomes a short circuit when a low voltage is appearing at its input. Then it becomes a short circuit. If a high voltage appears at its input, it remains an open circuit. So this switch is open. When a low voltage comes, the switch is closed. So this is the implication of the bubble. If there is no bubble at the gate, this means this transistor, the switch is closed when there is a high voltage appearing, and the switch is open when there is a low voltage appearing. So with this idea, we can now interpret this circuit. So you see the input A, when it is 0, that is low, when it is 0, so we will be using the digital symbols now, not low voltage and high voltage. For low voltage we know we are interpreting as 0, high voltage we are interpreting as 1. So when we have 0 as A as 0, then Q1 is on, Q1 is on, Q2 is off. That means VDD has appeared at C. So since VDD is a high voltage, C is giving you a value of 1. And when A is 1, then Q1 is off and Q2 is on. So then your VSS, which is the ground voltage, is coming to your C, which now becomes 0. So now if you simply look at the input and the output relationship, you will see that this is the not truth table. This is the not truth table. So this becomes a NOT gate. This circuit arrangement is the NOT gate. We will first look at the NAND. For implementing the NAND, we need 4 CMOS transistors. And you notice where the bubbles are. The bubbles are at Q1 and Q2, and Q3 or Q4 are without the bubble. Now you read the table. So when A and B are 0 and 0, then Q1 and Q2 would be on and Q3 and Q4 would be off. So your VDD is coming to C. So C becomes 1. When Q1 and when A is 0 and B is 1, then Q1 is on, Q2 is off. But since Q1 is on, your VDD is still coming to C. So your C has become 1. You can see that Q3 and Q4, one of it is off. That means the ground is not reaching C. Similarly, when A is 1 and B is 0, even then VDD would come to C because your Q2 is on. And since your B is 0, Q4 is off, so your ground is not able to come up to C. So ground is able to come up to C only when A and B both will be on. Then VDD is not able to come to C because both Q1 and Q2 are off. But since Q3 and Q4 becomes on now, the ground is able to reach up to C, and then C becomes 0. And now when you look into the input-output relationship only, you realize that this is a NAND gate. This is the NAND gate. We are of course talking about positive logic. So when I am not mentioning anything, it is a positive logic. So this is the NAND gate. Now the NOR gate. The NOR gate circuit arrangement is like this, and you can again do the analysis on this slide. You can see that when A and B would be both 0, then VDD will come to C. In all other cases, VDD will not be able to come to C, and the ground will come to C. So this becomes a NOR gate. Now what about AND gate and OR gate? I have come to Xor. So what about AND gate and OR gate? So you know that AND is basically not of NAND and OR is not of NOR. We have already studied NOT gate, NAND gate, NOR gate. So I am sure that you will be able to connect the NOT gate circuit to the output of this NOR gate, and the resultant output would be the OR gate output. So that circuit I am sure you will be able to draw up. So I have not covered it here. However, please expect this sort of questions in tutorials as well as examinations, which is not drawn here. I may ask you, and that would be very simple for you to actually come up with. So you simply connect this NOT gate, you simply connect at the terminal, at the output terminal of the NAND to get and to NOR to get OR. Similarly, if you want to get XNOR, you have to connect the NOT gate at this terminal. In that way you can do. There is also another way you can do, which I will ask you to explore. So after understanding the logic of this XOR gate, you will be able to perhaps construct a XNOR gate also without connecting a NOT gate at the output of XOR gate. So that sort of a question can also be coming. So now let us simply explore the XOR gate logic. Here you see the connections are like this, and you see that at the input, all the top transistors Q1 to Q4 are having bubbled gate, okay, and the bottom ones are not having bubbled gates. And what we have done, we have also connected A dashed and B dashed at Q3 and Q2 respectively. Also A dashed and B dashed at Q7 and Q8. So this is the arrangement. So I am sure that some of you are able to realize that other different types of arrangement can also be possible, since we are utilizing dashed as well as bubble. So there are a few other combinations which can be possible, but all of that will give the same result. So let us only look into this particular arrangement, and those who are not able to realize how other possible arrangements can be possible, they can simply remember this circuit and remember the derivation that will follow from this circuit. So now you see, if A and B are both 0, then look at Q7 and Q8. Q7 and Q8 will become on. So you see the Q7, Q8, I have actually taken them together now, since we are dealing with 8 gates. So you see that Q7 and Q8 has become on, and this immediately brings our ground voltage to C. So C will become 0, but we also need to ensure that the VDD is also not coming to C. Both high voltage and low voltage coming to the same terminal will lead to some problem. So in the case 0, 0, you will see both these branches will be off, because at least one of these transistors will be off. So like in Q3, Q4, when we have A as 0, then Q3 is off, and when we have and for B is B0, Q2 is off. So these channels are off basically. Similarly, you can analyze for 0, 1. So when we have combination 0, 1, then this channel becomes open. So this becoming 0 makes Q1 on, B becoming 1, B dashed is 0, so Q2 becomes on. So this channel opens and VDD comes to C. However, Q3, Q4 is off, but it doesn't matter because already I have been able to take VDD to C. But I should ensure Q5, Q6 channel is off, Q7, Q8 channel is off, and since A, B is 0, 1, you can easily read from this circuit that these channels will be off. Similarly, you can read for the other two combinations. You can look at the circuit and make yourself realize that the circuit, that these switch combinations are behaving in this off and on as written in this table. So verify, and once you have verified, you will realize that this circuit combination, what it is giving us is basically a XOR gate. The input output combination is the same as the XOR gate. Now the task that I will give you before leaving the lecture, yes, the lecture has ended, so before leaving the lecture I will give you the task to create a XNOR gate. Sorry, so you create a XNOR gate. It is obvious that if you connect a NOT gate at C, you will get a XNOR gate, but that will give you 2 additional transistors. I am asking you to create a XNOR gate using 8 CMOS only, and the arrangement will look similar to this. That I am giving you a hint. Arrangement will look similar to this. However, these signals which you have connected and the bubbles will change places. So that is where you have to actually see where you will keep bubbled transistors and where you will give the A B signals and A dash B dash signals. That will only change. And if you are able to actually if you are able to if you know this already, and if you express XOR as AB dashed plus A dashed B and then look at this circuit, and knowing that XNOR is AB plus A dashed B dashed, now I have given you enough hint actually. Now you will be able to directly see where you have to put your A dashed B dashed and where you have to put your bubbled gates. So this is left for you as an exercise, and probably I will also give it in the tutorial, so but you practice this for your own sake. So here I will leave you. So our understanding of gates are complete. So these are the only possible gates that we will work with. So we will have 2 or multiple. So we have only looked at 2 variable gates, and gates are actually 2 variable mostly, except you have already seen that we can have multi input OR gates. So the OR functionality does not get affected. Even the AND functionality does not get affected. So we can have multi-input gates, but the basic truth table of the gates are what is important. That should be the takeaway. The expressions for the gates, apart from AND and OR, the other gates, the expression of the other gates are something that you should always remember, and the gate symbols, logic gate symbols, are something that you should already develop a practice to draw properly. So these should be the 3 takeaways from this set of lecture. Thank you for your attention, and here I end the lecture.